In this session, continuing on with a concrete example of a superposed state in the context of the infinite square well with two energy eigenstates, one of this form that corresponds to the ground state energy, the lowest energy, and the next one, so an excited energy level, and its wave function is of this form. Okay, and we're adding two of them, so we're superposing two, and here's your coefficient, your C, C1 in this case, and this is C2, and this constant here is just to normalize, so the whole thing is normalized, right? And so this is your wave function, time independent, inside the square well, so your mod of x is less than a, so your square well limits, so the infinite barrier walls are at x equals a and minus a. Right? So so those barriers are impenetrable, so the u is 0 when x is outside that range, outside plus or minus a. Okay. Now that's the time independent form. If you use the full form with the time dependence, this is all revision in a sense. We've done this before. So here's your x part, your spatially dependent part. But here's the part that depends on time. So if you remember when we solved, way back early on in one of the early lectures, solving the Schrödinger equation, we split the wave function into two parts, a spatially dependent part and a time dependent part. Well, like here's the spatially dependent part and here's the time part, and that was one solution, let's say psi 1. And similarly, here's the spatially dependent part of a second solution, and with the time dependent part. And these two solutions were for different energies, different allowed discrete quantized energies, right? So energy E1 and energy E3. Now why 3, why not 2? Because in here we're talking about the infinite square well case, which we've done several times, for the case for odd integers, so 1, 3, 5. Okay, so 1, 3. Okay, so here's the full superposed quotient, wave function, depending on x and t, right, of this form. And from earlier work on solution to the infinite square well, your allowed energies, your quantized energies, took this form: n squared pi squared over h bar squared all over 8m a squared, right, for integers n, 1, 2, 3, dot dot dot. All right. Now, is this so we're assuming we have two solutions, and what we're trying to show is that combination is quantized. We'll try to show the probability, if you do a measurement, that you get the energy value E1 will be C1 squared, so it should be a half squared. We'll show the probability of getting the energy value when you measure the energy being E3 will be C3 squared, so in other words it'll be this squared, right? The sum of those two probabilities should be 1. Right? Because we only have two states here, so when we measure it and this wave function collapses to one of them, to either this one or this one, the probability that it's either of those has to be 1, because we only have two states in this general wave function, right? So we can check that it's normalized. What else can we do? We can then find the average value of the energy, the expectation value, given the probabilities, what do we expect the average value to be, so we can calculate that. And remember, in quantum mechanics, your expectation value is written with these angular brackets. So you put some observable, remember an observable is just some measurable physical quantity, position, momentum, angular momentum, spin, energy, etc. Right? Lots of examples of observables. So when you put an angular bracket around your observable, that means the expectation value of that observable. In other words, what's the average value when you measure it for that observable, in this case E. Alright? So okay, so that's the overview. So now let's actually do it. Now so the first thing, we have this superposed wave function of two wave functions that are your U. One of them is this, the other is this one. They are the allowed states. They're the solutions, two of them, two different ones, to your Schrödinger equation, to your STIE, in fact, your Schrödinger's time-independent equation, STIE. Okay, so we're using U in that when U is a solution to the STIE, the time-independent equation. But here's your equation for the more general form, when it's both spatially, x, we're talking one dimension here, and time as well. So it's more general. So let's start with proving that this wave function is normalized. In other words, if you square it and integrate it, you should get 1. And the interpretation of that is the probability of getting a result, either E1 or E3, is certain. I mean, you get one or the other. That's the only two possibilities. So, in fact, that's where this factor here came from. Is to ensure that this is normalized. When you square it and integrate it, you get 1. Hence this factor. Right. So in a sense, we're repeating what's already been done to get that factor in the first place. Okay. Right. So this is the sort of typical thing I ask you to do for homework. It's just just doing the mechanics, the cranking out the calculus, if you like. Take here's your psi, function of x and time. So plug this in to here. So well, I sort of skipped a line in a sense. This psi squared, you need to look on that as psi star. In other words, the conjugated form of psi. So this psi squared is psi star psi, right? So you'd need to, for the psi star, you'd need to change all the i's here to minus i's. So here you've got a minus I. So psi star would make that psi plus I, right? Minus minus, and similarly here, right? So then you multiply that by itself, except for the i's here now plus i's here and here, right? And so that gives you the square, and then integrate it over dx. Now x outside these wave functions here are 0. Outside the range, outside the well of width 2a, ranging from a to minus a. So these limits here, plus minus infinity, in fact, just become a to minus a because psi is 0 outside those limits, right? So I haven't even bothered writing HW. So it's sort of obvious. Do this yourselves. And you'll get, things will simplify down to this kind of stuff. Notice, there's no mention of time in this, right? The time factors here, these terms, the time terms, if you like, have been eliminated in the mathematics. They just drop out. So you're just left with spatially dependent terms. Okay, so you get that far. Now, if you then calculate this integral, you will get, I think it's just a, So this is just a, and this also is just a. Right? So this integral plus this integral gives you just the a's cancel. You just get 1/4 plus 3/4, which is 1, which is what you're trying to show. Right? So therefore.